Imagine two circles on a plane. As we bring them closer, they first touch at a single point. Move them a little more, and they intersect each other at 2 points. But here's something important. Two circles can never intersect at more than 2 points, unless they completely overlap. And that little fact unlocks a wonderful result. Through any 3 non-collinear points in a plane, there exists a unique circle, which means every triangle has its own unique circumcircle, a circle passing right through all 3 vertices. How do we find this circle? Well, think of a triangle's side as a chord of the circle. The perpendicular bisector of any chord must pass through the circle's center. So, draw the bisectors of 2 sides. And where they meet, that's the center of the circumcircle. Now here's where things get really interesting. It's not just the vertices of a triangle that give us such a circle. If we pick other groups of 3 points, the midpoints of the sides, and the feet of the altitudes, they too define a circle. And here's the mind-bending part. These two are the very same circle. This remarkable circle is called the 9-point circle. And now, 2 questions naturally arise. First, can we really prove that all 6 of these points lie on the same circle? Second, if we've only listed 6, where are the other 3 points hiding? Let's start with a simple fact. In any triangle, the line joining the midpoints of 2 sides is always parallel to the 3rd side. This comes directly from triangle similarity, and we're going to use it in different ways as we go along. Let A prime, B prime, and C prime be the midpoints of the sides opposite to the vertices A, B, and C. That already gives us something interesting. These midpoints connect in such a way that they form a parallelogram. Therefore, the opposite angles are equal. Next, drop a perpendicular from vertex A to the base BC, and let it meet the base at a point we'll call D. Now, let's focus on the right-angled triangle ADC. In any right-angled triangle, the hypotenuse acts as the diameter of its circumcircle, which means the center to its vertex is a radius. Therefore, B' is equally distant from A, C, and from D. This makes triangle D, B', C isosceles. So the 2 base angles are equal. That means D lies on the same circle as A', B', and C'. After all, in a cyclic quadrilateral, the opposite angles always add up to 180 degrees. But you might wonder, what if point D had fallen on the other side of the midpoint? Even in that case, the conclusion is the same. Because in a circle, a chord subtends equal angles at any point on the arc, as long as the point lies on the same side of the chord. Using similar reasoning, we can prove that points E and F lie on the same circle as well. But this circle still has secrets. The points where it meets the altitudes are no ordinary points. They are the midpoints of the line segments that join each vertex of the triangle to the orthocenter, the point where all 3 altitudes meet. And with that, the last 3 of our 9 points quietly appear. Let's pick one of those new points and call it P. Now, in the 9-point circle, the line connecting A' and P can be treated as a diameter. Since angle ADA' is already 90 degrees. Therefore, the angle A'C'P must also be a right angle. But here's a key observation. A'C' is parallel to the side AC of the triangle. So, if the angle at A'C'P is 90 degrees, then the line C'P must be parallel to the altitude BE. But in the triangle ABH, C' is the midpoint of AB, and C'P is parallel to the base of this triangle. Therefore, it follows that P must be the midpoint of the line segment joining A to H. And there it is, proved. Now, one might wonder, what is the radius of the 9-point circle? We know that the circumcenter is found by drawing the perpendicular bisectors of the triangle's sides, which essentially are its chord. In the same way, the perpendicular bisectors of A'D and C'F meet at the center, N, of the 9-point circle. This means that N lies exactly at the midpoint of the line joining the circumcenter, O, and the orthocenter, H. Now, focus on triangle AOH. since N is the midpoint of OH and P is the midpoint of AH. By similarity of triangles, we can say that AO is twice NP. But AO is the circumradius, and NP is the radius of the 9-point circle. Therefore, the radius of the 9-point circle is exactly half the circumradius. With this, we come to the end of our discussion about the 9-point circle. Thanks for watching. If you enjoyed this video, don't forget to hit that subscribe button and join us for more exciting and interesting lessons just like this.